Hello everybody, my name is Nate Rude. I work in Variscite's R&D software team. Today I'll be presenting how you can enhance your artificial intelligence and machine learning edge computing with Variscite system-on modules. This is our agenda for today. I'll start by giving an introduction to Variscite, highlighting our solutions for hardware accelerated machine learning. Then I'll give an introduction to artificial intelligence, machine learning, and deep learning. After this, we'll take a closer look at NPU hardware and software solutions, and I'll finish by sharing the next steps for how you can get started with machine learning. All right, again, I'll start with a short introduction to Variscite. Variscite is a leading system-on-module designer and manufacturer established in 2003 that targets the embedded products markets. Variscite has over 7,000 customers worldwide and is shipping over 2 million units per year with steady year-over-year growth. Variscite owns its production facilities with a total capacity of over 3.5 million units per year. Variscite is based in Israel and has local offices in Europe and North and South America. Variscite is committed to producing high-quality SoMs, which is demonstrated by its ISO 9001-2015 certification for quality management systems and ISO 1345-2016 certification for medical devices. As I mentioned, Variscite's a leader in ARM-based system-on-modules market with an extensive customer base and pipeline. Variscite has the most diversified ARM-based portfolio with extensive longevity and compliance policies. Additionally, Variscite was the first SoM vendor in NXP's Platinum membership and its partner on nearly the entire i.MX8 and i.MX9 product lines. Variscite is a trusted leader in the embedded market, delivering certified high-quality solutions with strong production capacity, stability, and lead times. Let's take a moment to explain what a system-on-module or SOM is. A SOM is an embedded computing module that integrates the essential components for embedded products. This includes the processor, memory, both the RAM and storage, power supplies, and other common elements such as Wi-Fi modules, Ethernet PHYs, audio codecs, and more. The key advantage of using a SOM is that Variscite takes care of designing and maintaining these critical and common components. This allows you to focus on developing your specific application and product. As illustrated in the image, the SOM is mounted on a carrier board. Variscite provides the source files for our carrier boards as references, which can be used and customized by our customers as needed. You'll also notice a heatsink in the image. Not all SOMs require heat sinks. It depends on factors such as the processor, the application, the load, and the environment in which the SOM is being used. Why should you use a Variscite system-on-module? Using a SOM provides faster time to market. It allows you to minimize your hardware and software development and testing phases. There's reduced R&D cost. You can avoid the high cost and risk of hiring your own design team. Scalability, Variscite's support of the entire i.MX8 and i.MX9 family allows for seamless scalability between SoCs within our pin-to-pin families for current or future products. You'll receive fully functional modules from Variscite all the time. No need to manage the complexities of manufacturing yourself. Variscite's hardware and software is production ready. We have BSP and driver support for multiple operating systems such as Yocto, Boot2Qt, Debian, and Android. In fact, our hardware and software is tested and used by hundreds of other customers. Variscite has free technical support for both hardware and software, allowing you direct access to R&D engineers using our customer support portal. Also, all of our software is open source on GitHub, and we have helpful guides and documentation on our software wiki. Our in-house production enables stable availability and lead times, and we have up to 15 years of longevity, so you can rest assured that you'll have long-term support from Variscite. Variscite has two SOM families. One is named the VAR-SOM, and the other is named the DART. On this slide here, you can see the VAR-SOM family, which offers scalability from the i.MX6 and 6UL, all the way up to the newest and most powerful processors like the i.MX8, 8M-PLUS, MX93, and also the TI AM62. In general, these SOMs are pin-to-pin compatible depending on your PinMux configuration. The SOM family has two SOMs with NPUs for accelerated machine learning, the VAR-SOM-MX8M-PLUS and the VAR-SOM-MX93. Variscite also has another pin-to-pin compatible family named the DART family. The DART family has a smaller form factor and provides more interfaces than the SOM family. It's also pin-to-pin compatible within its own family and supports scaling from the 8M Mini up to the newest MX95. The DART-MX95, DART-MX93, and DART-MX8M-PLUS all have NPUs providing hardware acceleration for machine learning applications. The Variscite SOM and DART families provide scalability and processing capabilities while maintaining the same interfaces and form factor, allowing you to scale from the Cortex A7 and A9 up to the A53 and A55 depending on your product requirements. Again, Variscite has multiple SOMs with integrated NPUs, providing hardware acceleration for machine learning applications. We have the DART-MX95, we have the DART-MX93 and VAR-SOM-MX93, and finally we have the DART-MX8M-PLUS and VAR-SOM-MX8M-PLUS. We have evaluation kits for each of these SOMs that are available to order from Variscite.com. Let's look a little closer at Variscite SOMs with NPUs. The DART-MX95 is Variscite's newest and most powerful SOM. It features up to 6 Cortex A55 cores and is perfect for running demanding operating systems like Linux or Android. Additionally, it includes 2 real-time coprocessors, the Cortex M7 and Cortex M33. It features an integrated NPU designed by NXP, which is optimized for AI and machine learning. On the networking side, this is the first Variscite SOM to support 10 gigabit Ethernet, as well as dual gigabit Ethernet. It also supports Wi-Fi 6, Bluetooth, and 802.15.4. For multimedia and graphics, the DART-MX95 boasts a 2D and 3D GPU and advanced image signal processor. The DART-MX95 supports up to 16 gigs of RAM and 128 gigs of eMMC, and is Variscite's most powerful machine learning processor, all in a small DART form factor. On the other end of the spectrum is the VAR-SOM-MX93. The VAR-SOM-MX93 has a less powerful dual-core A55 processor with a single Cortex M33 coprocessor. It also features an NPU for machine learning acceleration. However, it is the least powerful compared to the MX8M-PLUS and MX95. The MX93 supports dual gigabit Ethernet and the same Wi-Fi 6, Bluetooth, and 802.15.4 as the 95. It does not have a GPU or ISP. However, it does have a 2D pixel accelerator, which can help with some simple graphics acceleration. Even though there's no ISP, the MX93 still supports camera inputs and display outputs, but any encoding or decoding and rendering will be performed in software. If you're familiar with the MX7, the MX93 is an upgrade to the MX7 with the addition of the NPU, more powerful processors. And if you're familiar with the Nano, it's a little bit less powerful than the Nano, but adds interfaces like dual CAN, dual USB, and native LVDS display. The DART-MX93 is basically the same as the VAR-SOM-MX93, except that it has a smaller form factor and is part of the DART pin-to-pin family. As I mentioned before, although the DART family is a smaller form factor, it actually exposes more pins and peripherals on its connectors. And finally, we have the VAR-SOM-MX8M-PLUS. In terms of both CPU and NPU performance and cost, the 8M-PLUS falls in the middle between the MX93 and MX95. The 8M-PLUS has a quad-core Cortex A53 processor and a Cortex M7 coprocessor. It also supports dual gigabit Ethernet, Wi-Fi 6, Bluetooth, 802.15.4, USB 3, CAN, and has both a powerful GPU and image signal processor. And we also have the DART-MX8M-PLUS, which is very similar to the SOM, but again has a smaller form factor. It's worth noting that all Variscite's MX95, MX93, and 8M-PLUS SOMs feature a -40 to 85 C industrial temperature range and 10 to 15 years of longevity. All right, thanks for listening to the introduction to Variscite. Now I will introduce artificial intelligence, machine learning, and deep learning, and share some of the key concepts to know when getting started. Okay, let's first look at the different categories of artificial intelligence. AI, which started around 1950, involves creating machines that can perceive their environment and act to achieve specific goals. It's about making machines smart. In the 1980s, machine learning, or ML, emerged as a subset of AI. Instead of programming machines for every task, machine learning enables them to learn from data and recognize patterns. This means machines can improve their performance over time with more data. Then in the 2010s, deep learning, or DL, became more prominent. DL uses artificial neural networks to mimic the human brain, with multiple layers of algorithms processing information. This allows machines to solve very complex problems, such as image and speech recognition. DL is the technology behind many advanced applications we see today, like self-driving cars and sophisticated language translation services. So AI is the broad field from the 1950s. Machine learning brought learning from data in the 1980s, and deep learning added neural networks in the 2010s for advanced problem solving. All right, there are three main concepts I want to introduce about AI and machine learning. The first is to conceptually compare traditional programming to machine learning. With traditional programming, we input some data and a set of rules and we get answers. For example, if we want to know if an object is an apple, we have to write our own logic to check if it's round, check if it's green or red, etc. We use a fixed set of rules. With machine learning, instead of writing our own rules, we input a large data set with answers, and the output is rules, or in other words, a trained model. So we might feed the algorithm with 100 pictures of apples, and the algorithm determines its own set of rules. Machine learning models are a mathematical representation of rules that can be used for identification in image recognition, speech recognition, anomaly detection, and much more. These models learn pattern from data and then use these learned patterns to make predictions or identify patterns in new data. This makes machine learning especially effective for applications where determining the set of rules is a very complex task. So for example, what if I tasked you with determining if an image was a pumpkin or a basketball or an orange using traditional programming? You would need to write a lot of fixed logic to determine which is which. With machine learning, you can train a model on many images of pumpkins, basketballs, and oranges, and it can easily predict the answer for any given image. The second main concept to understand in machine learning is inference. Inference is the process of using a trained model to make predictions or decisions based on new data. The NPU is specifically designed to accelerate inference time. Let's take a look at a typical machine learning application development workflow. The first step is to prepare the data and train the model. This involves gathering a large amount of data, labeling it or otherwise preparing it in a way expected by the model, and then feeding it to the model. This is normally done on a very powerful computer or server and does not use the NPU. The next step is to validate the model. This is an iterative process of tweaking the dataset and model parameters to ensure the model performs well in your application. After fine-tuning, the model needs to be optimized and converted and quantized to match the precision requirements of the NPU for the specific SoC. Note that this can change the behavior of the model, so the final validation must happen on the target hardware. Finally, the model is deployed on the target device. The model and any new data are loaded onto the NPU, which performs the inference and makes predictions. Again, the NPU is designed to accelerate the inference time, which is the process of using a trained model to make predictions or decisions based on new data. Let's revisit the problem of determining if an image is a basketball or an orange. Doing this with traditional programming logic can be quite difficult. However, with machine learning, it can impressively become a very simple process. As discussed in the previous slide, the first step is to train a model with the dataset. Here, our dataset consists of labeled pictures. We can train a machine learning algorithm like CNN, ResNet, or MobileNet using labeled pictures of oranges and basketballs. This training process creates a model capable of predicting if an image is a basketball or an orange. After training the model, we can feed new images to the model and it will predict if the image is an orange or a basketball. It's important to remember that training is computationally expensive and is usually performed on multi-core systems and GPUs. However, the inference, which is the process of making predictions with the trained model, is much less expensive and can be deployed on resource-constrained devices like a Variscite system on module. Note that this is an example of a specific type of machine learning called image classification, which falls under classification and supervised learning, which are both subfields of machine learning. There are many different fields of machine learning and ways to train models, and not all algorithms require the data to be labeled like in this example. I want to spend a few more minutes talking about inference. Again, inference is the process of using a trained model to make predictions or decisions based on new data. Inference can be done either on the cloud or locally, often referred to as on the edge. For example, when you ask a large language model like ChatGPT a question, your question is sent to the cloud, processed, and then the answer is returned to you. On this slide, we're going to look at two examples where a camera takes a picture of a basketball and displays on the screen that it's a basketball. On the left, the picture is sent to a cloud, which performs the inference. The main advantage of using the cloud is that it has unlimited computing power. However, this means your application must have a network connection, might experience higher latency, and will incur cloud compute and maintenance costs. On the right, the inference is done using the NPU on a Variscite SoM. This offers increased privacy and security since the data never leaves the SoM. It also allows for lower latency as there are no network delays. It requires lower power. It doesn't need a network connection. The consideration here, though, is that the NPU has limited processing power compared to the cloud, which is why it's crucial to train and fine-tune the model for your specific application. All right, so if you're like me, you're probably thinking, cool, but how do I actually do this? Well, NXP's EIQ toolkit and portal provide an end-to-end solution for the model development and deployment. It's out of scope for this webinar, but you can visit NXP's website to download the EIQ tool and its related documentation. As you can see in the screenshot, it even shows how to train a model using photos, just like we've been discussing. The EIQ toolkit and portal have everything that you need to train, optimize, and deploy a model on a Variscite system on module. It supports pre-trained models and allows you to bring your own model and data for transfer learning. The intuitive GUI simplifies machine learning development for developers of all experience levels, enabling you to create, optimize, debug, and export models. You can import datasets, rapidly train and deploy neural networks, and the output is compatible with major inference engines like DeepView-RT, TensorFlow Lite, Glow, and ONCs. Plus, it includes models for object detection, image classification, and more. This comprehensive toolkit makes it much easier to implement machine learning on edge devices. All right, next, let's take a closer look at NPU hardware. First, let's talk about the different types of cores that can run AI-related tasks. First, we have the CPU, or central processing unit. CPUs are general-purpose processors. They're very versatile and can handle a wide variety of tasks, but they're not specifically optimized for AI or machine learning workloads. Next is the GPU, or graphics processing unit. GPUs are optimized for parallel processing and rendering graphics. They excel at tasks that can be broken down into smaller parallel units, which makes them useful for some machine learning applications. However, while GPUs are powerful, they're not specifically tuned for machine learning tasks. Finally, we have the NPU, or the neural processing unit. NPUs are specialized processors designed specifically for AI workloads. They efficiently handle complex neural network computations and are optimized for machine learning tasks. A key point to remember is that operators not supported by the GPU or NPU will default to running on the CPU. This ensures that even if the GPU or NPU can't handle certain tasks, the system will still perform those operations using the CPU. When we talk about hardware accelerators for machine learning on the edge, you might come across a variety of names. These can include terms like neural processing unit, an AI accelerator, neural accelerator, a deep learning accelerator, a neural compute unit, etc. Despite these different names, they all basically have the same purpose, which is to perform efficient matrix operations required by AI tasks. As a reminder, Variscite has system on modules for all three NXP SoCs with integrated NPUs. The VAR-SOM-MX8M-PLUS and DART-MX995 with the 8M-PLUS processor use a third-party NPU with 2.3 TOPS from Variscite. The VAR-SOM-MX93 and DART-MX93, again, they use a third-party NPU with 0.5 TOPS from ARM. And the newest DART-MX95 with the i.MX95 processor uses an in-house Neutron NPU from NXP with 2 TOPS. I want to highlight that NXP's first two SoCs use NPUs from third-party vendors, while the newest i.MX95 processor uses an NPU designed internally by NXP. This allows NXP to own and maintain both hardware and software to improve integration and also support its longevity program, which is often more than 15 years. So moving forward, NXP's plan is to use the in-house on-die acceleration for its newer SoCs. If you were paying attention in the previous slide, you might have noticed that the older i.MX8M-PLUS has 2.3 TOPS, while the newer i.MX95 has only 2 TOPS. At first glance, this might suggest that the MX95 NPU is less powerful. However, the MX95 is actually 2 to 4 times faster in modern applications. TOPS, or trillions of operations per second, measures the peak performance of an AI processor, how many operations it can theoretically perform in 1 second. However, TOPS alone doesn't always reflect real-world performance. This is because the MX95 uses NXP's in-house Neutron NPU, which is optimized specifically for modern AI workloads. Unlike the i.MX8M-PLUS, which relied on third-party IP, the i.MX95's NPU is designed to handle today's neural network models far more efficiently. The Neutron NPU is optimized to execute modern AI algorithms with fewer clock cycles per operation, resulting in significantly faster performance. It features advanced data management techniques that reduce bottlenecks, enabling higher sustained performance. Additionally, the i.MX95 incorporates specialized hardware blocks that accelerate common AI operations and more efficient pipeline architecture that processes multiple operations simultaneously. Thanks to these improvements in algorithmic optimization, data movement, and processing techniques, the i.MX95 outperforms the 8M-PLUS despite having fewer TOPS. So while its TOPS rating is slightly lower, the MX95 is actually a much faster and more powerful AI processor, better suited for modern AI applications. NPU applications vary in complexity and hardware requirements. This chart, which is created by Variscite, provides rough guidelines for the amount of TOPS required by different AI applications and overlays this with the TOPS capabilities of the MX93, 8M-PLUS, and MX95 NPUs. Starting at the bottom, we can see that regression, classification, and clustering tasks are typically more basic and generally only require around 0.5 TOPS. These tasks are suitable for all SoCs, including the MX93. As we move up in complexity to applications like anomaly detection, image classification, and object detection, the demand for TOPS increases. In these cases, the MX95 or 8M-PLUS might be more suitable. However, this isn't a hard rule. The MX93 may still be capable of performing these tasks depending on the level of optimization applied and the performance requirements of your application. And then further up the chart, we transition from machine learning into deep learning tasks like object tracking, segmentation, and generation. These tasks require even more TOPS, which can push the limits of even the 8M-PLUS and MX93 NPUs. Again, I want to emphasize that these are not strict limits, but rather guidelines to help determine which NPU might be most suitable for your application. Additionally, it's important to note that while the MX95 has fewer tops than the 8M+, again, it includes optimizations and hardware accelerations for certain machine learning algorithms, making it 2 to 4 times faster in some cases. So as we always recommend at Variscite, whether you're working with multimedia or graphics or the NPU, it's best to benchmark your application on the actual hardware to ensure that it meets your requirements. Now let's look a little closer at the NPU software. Let's start out with an example. Here we have examples of 3 different image processing applications: image classification, object detection, and object tracking. On the left is image classification, where the model assigns a label to the entire image, identifying the most prominent object. In this example, the overlay shows 3 different probabilities: a sports car, a convertible, and a racer. On the i.MX8M+, the inference time is about 2.9 milliseconds. In the middle is an object detection application. The model identifies and labels multiple objects within an image, such as a dog, a person, or a bicycle. This is a much more complex task, requiring about 12 milliseconds on the 8M+. And on the right is an object tracking example. This task is significantly more complex, involving deep learning to monitor and follow the movement of objects across multiple frames in a video. The model determines things like the object's trajectory or potential collisions. For example, maybe the model will track the suitcase to see if it's left behind by the owner. An application like this could take 1,000 milliseconds or more on an 8M+, so significant optimization would be required to ensure the platform is suitable. The 8M+ and also the MX93 and MX95 can handle a range of image processing tasks, but the complexity of the application directly impacts the processing time, emphasizing the importance of careful optimization and hardware selection. This slide provides an overview of various AI and machine learning and deep learning tasks, highlighting the complexity levels, the typical models, and the estimated tops required for each. Again, while these tops values serve as useful guidelines, they're not strict limits. The suitability of an NPU for a particular task depends on multiple factors, including the specific model used and potential optimizations. For example, regression, classification, and clustering models can require less than 0.5 tops and are likely suitable for the MX93, 8M+, and MX95. However, moving beyond this to more complex tasks like object detection or facial recognition that require 1 to 2 tops or more, the 8M+ and MX95 become more suitable. Whether you're working with basic tasks like regression and classification or more complex ones like object detection or facial recognition, this table can be used as a guideline and a starting point to help you know what you can expect from each SOM and some of the typical algorithms and models and use cases that are available. Here's another table showing even more complex deep learning tasks like object tracking, segmentation, image generation, and text understanding. These applications and models require more processing power, so it's important to consider if an embedded NPU is appropriate for these applications. Again, I don't want to draw a hard line in the sand and say it's not possible. Depending on your application and again how well you can optimize your model and how long of an inference time is acceptable to your application, you may have success with one of these models. The table is just meant to compare the different applications and estimate the level of complexity that you have so you can have realistic expectations for the NPU. For example, you're not going to create ChatGPT-4 using an embedded system on module, but you might be able to do some targeted text processing similar to the tools you see on modern phones. Earlier in the presentation, I mentioned that it's possible to run inferences on the CPU, GPU, and NPU. Different software stacks and libraries support these capabilities depending on the specific NXP SoC. All Variscite SOMs in the i.MX8 and i.MX9 families can run inferences on the CPU. For GPU-based inferences, all i.MX8 SOMs except for the 8M Mini support the VX delegate. The 8M+ in particular offers hardware acceleration on the NPU using the VX delegate. The i.MX93, although lacking a GPU, provides hardware acceleration on the NPU using the Ethos U delegate. And lastly, the i.MX95 supports hardware acceleration on both the GPU and NPU using the Neutron delegate. All right, now that we've discussed all the theoretical information, let's look at a real world example and compare the performance using the CPU and NPU on the VAR-SOM-MX8M-PLUS, the VAR-SOM-MX93, and the DART-MX95. For this benchmark, we use the MobileNet model from NXP to do image classification. This processes an image and assigns a single label to the entire image, indicating the most prominent object or scene. On the scale of complexity, this is a relatively basic task. As expected, using either CPU or NPU, the VAR-SOM-MX93 was the slowest, with the VAR-SOM-MX8M-PLUS in the middle, and the DART-MX95 being the fastest. The inference time for the VAR-SOM-MX93 using the CPU is 149 milliseconds, and when using the NPU, it's reduced to only 4 milliseconds. This is a huge performance improvement. The NPU is over 37 times faster than the CPU, and this is a perfect example of how the NPU is designed to efficiently perform machine learning operations compared to the CPU. The inference time for the VAR-SOM-MX8M-PLUS on the CPU is 39.9 milliseconds and 2.9 milliseconds on the NPU. Again, this is a huge improvement, with the NPU being over 13 times faster than the CPU. And finally, the inference time for the DART-MX95 on the CPU is only 16.6 milliseconds and 1.2 milliseconds on the NPU. Again, even though the MX95 CPU is very powerful, the NPU is still over 13 times faster. So in the end, this is just one example. It shows the performance progression between the MX93, the 8M Plus, and the MX95. And it also demonstrates that while the raw tops of the 8M Plus NPU is more than the MX95, the specific algorithms optimized by the NPU and the overall performance of the SoC can result in greater machine learning performance. I presented a lot of data in this webinar, and the estimated number of tops recommended for different machine learning applications and models. However, as with any application, I always suggest you run your actual application on one or more Variscite evaluation kits to determine which has the right balance of performance, cost, and functionality for your application. All right, now let's look at the next steps for how you can get started. As I mentioned earlier, the EIQ toolkit and portal have everything you need to train, optimize, and deploy a model on a Variscite system on module. It supports pre-trained models and allows you to bring your own model and data. The intuitive GUI simplifies machine learning development for developers of all experience levels, enabling you to create, optimize, debug, and export your models. NXP also has machine learning user guides, as well as a nice presentation demonstrating how to debug and optimize machine learning models. So if you're just getting started with machine learning, these resources are the best place to start. Variscite has created a Python API which is designed to help beginners explore the machine learning field and develop their own applications by using cameras, displays, and user interfaces. The Python API has a quick example section where you can follow the links to download examples like image and video classification and detection from a dedicated GitHub repository on VeriGit. If the API is new to you, I encourage you to review our blog post, which goes into more detail than I can right now. There are also some other webinars and blogs from Variscite that you can review. We have a webinar about embedded machine learning applications on Variscite system on modules, which introduces some other topics about machine learning. We have a webinar that introduces we also have a blog post that walks through the steps of developing your own machine learning application using Variscite system on modules. These are just a few highlights. Beyond this, we also have many other webinars that are very helpful for getting started with all phases of development. So I encourage you to review them to see if any will be helpful for you or your team. And finally, you can visit our product website at variscite.com. You can contact our sales team at sales@variscite.com. You can contact us through our website, You can view our guides on our developer wiki, and you can view all of our open source code at github.com/varigit.
Thank you for joining the webinar. I hope you learned something.